Thank you. Thank you all. For those of you who are wondering why I've spent part of the day walking around with my sunglasses on inside or dressed like a pirate, I scratched my eye. So I'll say that now so I don't have to keep explaining it to every person I run into. So forgive me if I point kind of semi-wildly because things are a little blurry at the moment. But in any case, I want to talk to you about work that's been ongoing for the last year, and we're finally ready to publish some of the initial results. Exploring cosmological simulations with much more detailed models for stellar feedback on the ISM. And this is work with a number of collaborators at Berkeley, UCSD, and Irvine. And most of you here are very familiar with what we've been working on for the last couple of years. So this is very much built on that, and I don't really have time to review the details. But essentially, starting from a series of projects looking at isolated galaxy simulations, we wanted to do better and to try and remove some of the subgrid degrees of freedom that we have in our feedback and star formation models. So this is a simulation from this series that we've published papers on in the last few years of an SMC mass dwarf. You're looking at the gas surface density, and there's molecular gas in blue, warm ionized gas in pink, and hot gas above 10 to the 6 K in yellow. So what's included here? Well, sorry, came in the wrong order. So essentially, we've taken advantage of the fact that we have the benefit of Moore's law and can run very high resolution simulations. So the cosmological simulations I'm going to describe, cosmological simulations have resolution of 1 to 10 parsecs. 1 for the dwarfs, 10 for the Milky Way mass galaxies. Not as good as these isolated simulations, but still, I think, good enough to start resolving some of the structure in the ISM. You, of course, want to include molecular metal line cooling, all the cooling physics that we think we understand, so that you have very cold gas. And you can restrict star formation to very high densities, and people have talked about why that's important. At least we can say, while we still don't have any idea in these simulations how individual stars form, we can restrict star formation. In the canonical runs I'm showing, our density threshold for star formation is 100 particles per cubic centimeter. In addition, the gas has to be molecular and locally self-gravitating for it to form a star. But this is well above the mean ISM density, and importantly, also above the mean density even in molecular clouds. So these are the regions where we think stars will form. And also importantly, our assumed star formation model, while totally arbitrary basically, is that in this high density self-gravitating molecular gas, stars form at a rate of 100% per free fall time. So if star formation comes out inefficient, it is not a product of us putting in by hand a slow Kennicut-Schmidt law. And I'll show you that explicitly in a minute. Anyways, given that, you want to include physical sources of stellar feedback. And the main idea here is to, again, tag these to more explicit physical models. So you essentially take starburst 99, you take your favorite stellar population model here at Krupa IMF, and as a function of time, you explicitly track all of the following quantities. You track the supernova rate, and you say for every time step, what's the probability of a supernova going off? We individually, discretely resolve supernovae. There's not more than one supernova per particle per time step in these simulations. You separately tag whether they're type 1s and type 2s, and when one goes off, you inject the appropriate energy, momentum, mass, and metals according to your favorite stellar population synthesis model. Likewise for stellar winds, every time step you track both O-star and AGB winds. You follow your best guess of how to model photoionization from local ionizing photons and photoelectric heating. And again, critically, as Mark made the point, momentum is what really matters for stirring this stuff up and potentially ejecting it, so you follow all the sources of momentum. The ejecta momentum of winds and supernovae, and the momentum associated with radiation pressure. And Mark just gave a very nice talk all about this tau IR factor. For the cosmological runs I'm going to describe, we could easily get into a whole conference about tau IR. This is basically irrelevant, because I'm not resolving the dense gas where I would argue tau IR actually matters. For all the popular perception, Mark and I actually don't disagree that much. And I would agree with him completely that this is largely important in those dense regions around star clusters where sort of nascent supernovae form, but where these cosmological simulations simply don't resolve. So this, in practice, is never bigger than 1 or 2 in these simulations I'm going to show. But I will argue that this direct component is important for exactly the reason that we just discussed, that you've got stuff that's thrown up already in a fountain and can see some continuous acceleration. So anyways, with all that preamble, here's the result of one of our first simulations. This is a Milky Way mass halo forming. This is the gas. These are the stars. This is a mock Hubble UGR, or sorry, SDSS UGR composite. On the right, the gas is, green is warm ionized gas, red is hot gas above 10 to the 6 Kelvin, and the magenta, which is a little hard to see in the projection, is molecular gas, or molecular and atomic gas below 1,000 Kelvin. And you're looking at a region that's a constant physical couple hundred kiloparsecs on a side. So it's quite big relative to the galaxies at high redshift, but comparable to the virial radius at z of 0. And what you can see already is actually things were extremely violent at high redshift with very strong outflows shredding a lot of the IgM. Things by z of 1, really below z of 2, have started to calm down quite a lot. A hot halo has started to set up where you've got a lot of virial temperature gas, and the inflows are much smoother. Though there's still violent starbursts that are belching out material, you set up a much more well-organized disk at these late times as the accretion is more quiescent and there's less violence in the growth of the system.
Late accretion, that's the cooled gas actually is still the cold flow coming out from the, can you trace that as well?
Yeah, so this is a fully cosmological zoom-in simulation, so you have the large-scale filamentary structure, and certainly that's what's fueling the halo. For now, I'll abstain from whether or not those little filaments coming in are, strictly speaking, the cold flow punching through without ever heating up, or whether they technically heat up at sort of a third of a virial radius and cool back down quickly. We're trying to investigate that detailed question, but that's a sort of second-order aspect of the question. I'd say to lowest order, the halo is still being fed by these big filaments. The death of cold flows that some people have announced is premature, I'd say. But in any case, this is the late time galaxy. For those of you who are curious, this is one of the Agora initial conditions, actually. This is the 10 to the 12 solar mass halo from Agora. The non-busy merging history, although it actually ends up having this merger that's not quite done at z of 0. So. I don't have the picture of that. It looks by eye reasonably good. We haven't actually done a proper photometric mock to say what the scale height is. I suspect it's probably a little thicker than the actual Milky Way. So this one is 10 physical parsecs. Yeah. And 5,000 solar mass particles. Yeah. So because apparently our cosmological simulations have to have acronyms. We're calling this the FIRE project, for feedback in realistic environments. So let's look at some of the results. We can make very pretty movies. That's a prerequisite for any simulation. But so let's look at something like the Kennecott-Schmidt law and ask, is star formation inefficient in an instantaneous sense? And then we'll ask about the integral sense cosmologically. So this is the usual observed relation, surface density of gas, surface density of star formation. The shaded yellow area is basically the observations. And I've just plotted all our simulations at all different redshifts on there. And remarkably, things actually look quite good. And I really want to stress that we haven't tuned any parameters. There's no fudge efficiency parameter in front of the numbers we're putting in. The implementation is by no means perfect. You could definitely do better on everything we're trying to model, but we're not, multiplying the supernova rate by 3 or the energy by x. It's just taking the numbers directly out of Starburst 99, and the purely algorithmic aspects of the implementation are all designed to reproduce simple test problems, not, twiddled to reproduce this. This is exactly the code run on those isolated galaxies from the last couple of years, but just run cosmologically, adding in the 1 plus z's where you needed them. Added them in wrong at first, and everything exploded. So that one's an easy one. So the input efficiency is 100% per freefall time. Sure. Well, if you do no feedback simulations, you get 50% per freefall time. You'll always get order unity per freefall time absent feedback on a galactic scale. Locally, sure, you could make it 1%, you could make it 100%. You'll get the same answer for the global scale because the gas on large scales absent feedback will always collapse to higher and higher densities. And within the high density gas, the freefall time is incredibly short compared to the galactic freefall time. So in fact, if I run these simulations with no feedback, here's the results I get. About a 50 times higher star formation rate per freefall time. And to more specifically answer your question, give me one slide and I'll come back to your question. I think the reason for this is very simple, and many people have argued for this. Recently, Claude Fauché-Giguère and Shetty and Ostraker had several papers making variations on this argument. Essentially, absent feedback, things cool and dissipate. The momentum, that's the turbulent momentum that's holding everything up, gets dissipated on a crossing time. So you essentially get rid of your momentum, you shock and dissipate it at a rate that's equal to the total gas momentum, the gas mass, turbulent velocity dispersion, divided by the crossing time. You can just write that in terms of galaxy parameters here. I don't really need to go into what those are. And essentially the argument is just that that's the rate at which you're dissipating. Collapse will stop, you'll reach equilibrium when you're pumping in enough momentum from feedback to balance that rate. You'll at least then achieve some statistical equilibrium. So you have some input rate of feedback momentum from stars equals this dissipation rate. The input rate we expect is a few L over C. As Mark pointed out, radiation pressure, even ignoring this tau factor, gives you 1. But actually, the momentum flux from supernovae is also basically L over C. And the momentum flux from stellar winds is basically L over C. So even a conservative estimate of this gives you a few L over C. So some number times the star formation rate is really all that L is. And so you plug those together and you get the Koenig-Schmidt relation. That's all this is. And the only constant here is this efficiency set by actual stellar evolution models, not by galaxy physics, of the ratio of mass you put into a star versus energy you get out.
What was little sigma?
So little sigma is the velocity dispersion. So there is a residual dependence. So the Fauché-Giguère paper, essentially the whole point of the paper is trying to argue that observationally this residual dependence is there, basically. And I think you can debate that based on whose observations you use. And in particular, the infamous XCO comes in and basically decides how well or poorly this model actually works. But yeah, that's at the second order level. So anyways, as a consequence of this, one of the very nice things that comes out when you start explicitly treating feedback this way is that the star formation rate in your galaxies, while dependent very sensitively on feedback, is totally independent of this admittedly arbitrary small-scale star formation model and efficiency I put in. That doesn't appear in the equation I just described. Basically, as long as gas can cool, it will continue to collapse to whatever my density threshold is. And whatever the efficiency is there, it'll pile up until it forms enough stars to balance dissipation. And that's explicitly shown in these runs. These are different galaxies, star formation rate versus time, where I've just wildly changed this microscale star formation model. I changed the normalization by a factor of 100, or 20 here on the left. I changed the power law scaling with density. I changed the critical density above which I allow star formation. It has essentially no effect on the equilibrium star formation rate of the galaxies. So that's really reassuring because it tells us that these instantaneous star formation rates are becoming predictive on galactic scales in a way that is really important for making progress. So what about winds? And that's what we really want to focus on with the cosmological simulations. So if I look at the isolated simulations, an important thing that emerges is that the winds depend non-linearly on a combination of feedback mechanisms. Because of things like Piero just brought up in Mark's talk, you could have radiation pressure disrupt the interior regions of a molecular cloud, and then the environment a supernova goes off in is very different. So its coupling to the gas is very different. And these sorts of mechanisms play out in our isolated simulations, and I'll show you. I'm going to move very quickly through this slide, forgive me, because this is from the older work to show you what's, and I want to show you what's in the cosmological runs. But this is just an illustration in several different isolated galaxy simulations. The black line is the total wind mass loading, just defining wind in these toy model isolated galaxies as the mass that's escaped from the halo versus the total mass in stars form. So this is the sort of mass loading of the wind in each of these runs of different types of galaxies. The black line's what I get when I include all these feedback mechanisms. The red line's what happens if you remove radiation pressure, and of course things are lower. The blue line's what happens if you remove supernovae and stellar winds, and of course the lines are lower. They depend, how much lower depends on what type of galaxy you're looking at, and I don't have time to talk about the differences in these models at the moment. But the point I make showing this is simply that if you add the blue and the red lines, where I've taken the identical model and just removed one feedback mechanism in each of them, they should, if feedback were a linear process, these should sum up to actually more than the black line, because they still have most of the other feedback mechanisms in place. And in fact, they don't. They tend to sum to significantly below the black line, because there's these nonlinear interactions. So generating galactic winds is a nonlinear process, and one feedback mechanism is insufficient. And your idealized toy models studying each feedback mechanism in isolation do not capture the full dynamics of how you actually accelerate things out of galaxies. That's the qualitative point I want to make. So what happens in the cosmological context, being aware of this nonlinearity? Thank you. So here's zooming in on another Milky Way mass galaxy in a simulation without feedback and with our full feedback models. And this is just a map of the temperature, so the bright regions are hot, basically. And so unsurprisingly, feedback generates big winds that blast out and heat up big parts of the IGM. Okay, it's not surprising that that doesn't happen in our no feedback run, but it's good to check that there are big outflows. Quantitatively, what do those outflows mean? Well, the 0th order indicator we can look at is the galaxy masses and their relation to their halo masses. So this is sort of the 0th order punchline plot from the early results from these simulations. This is the galaxy mass stellar mass relation at z of 0. The cyan and purple lines are the observed estimates from both Baruzzi and Moster. And the dotted line is just if you turned all the baryons into stars, which something like that is what you get with no feedback, maybe half of that. And again, remarkably encouragingly, things actually work not badly with this simple model without having to retune everything. They may or may not be working up at high masses. I'm happy to discuss that later. We don't have AGN feedback, so even if the masses are reasonable, none of these galaxies is red and dead. They all have a quenching problem still. They're all booming star formers at z of 0. So it's definitely still problems up there. But things are at least in the right ballpark. And that's encouraging to me. And then you can look at this as a function of redshift, and things, again, don't look crazy, although the observational constraints, as you can see, as you go to high redshifts, don't extend to very low masses. So the comparison is pretty limited. I do want to mention just very briefly that this doesn't depend very much on purely algorithmic or numerical aspects. There are significant differences. You can change the masses by a factor of 2 by going between our new fancy SPH that includes all the newest sophistications from the last few years and gives very comparable results to the best cutting-edge grid codes in a lot of test problems. You can go from that, throw that out, just use crappy old Gadget 2 that we know has all these mixing problems, etc. You get about a 50% change in the galaxy stellar mass at late times. It's not that big a deal. You can change the density threshold for star formation from 10 to 1,000. You get factor of 2 sort of changes in this stellar mass. These are all significant, but they're not orders of magnitude, which is what happens if you start removing feedback elements. So this is that same plot where I take out different pieces of the feedback. So if I take out feedback entirely, these black circles, I basically turn nearly all the baryons into stars. But you can see it's almost as bad if I just take out one of the feedback mechanisms. If I take out supernovae, I run the same model but no supernovae, it's a disaster. I overpredict the stellar mass by an order of magnitude. But it's just as bad if I remove radiative feedback. In this case, the radiative feedback is removing both radiation pressure and photoionization heating. Because the dense regions don't get disrupted, the supernovae overcool in them. Also, the dwarf progenitors massively overcool because photoionization pressure is very important in these small dwarfs for regulating their star formation. It's a mess. So again, clearly the nonlinearity of these different feedback mechanisms interacting is important. And it's critical to include more than just supernovae. And I think that's reflected in the comparison to other simulations. So we're going to hear, we've already started to hear a little, and we'll hear a lot more tomorrow about new generations of simulations that are starting to try and include some of these feedback mechanisms that we've been harping on for a couple of years now. And I think they show a lot of the same qualitative improvements. So if you look at the M-Gal-M-Halo relation at Z of 0 here. This shaded gray range is our simulations, and these colored points are historical simulations by the groups. There's a problem at dwarf masses where the dwarfs are much too large in mass, even for models that got reasonable agreement at Milky Way masses. And as many of us here are well familiar with, the problem got a lot worse when you went to high redshifts. So here's Z of 2 to 3 plotting the same subsets of simulations. And again, even the simulations that looked really good at Z of 0 are, way up here in terms of way too much baryonic mass turned into stars at high redshifts. And that seems to be strongly suppressed with these new models. And many people, I think with the newest subgrid models, are finding the same thing. And the real key seems to be this early feedback, basically these mechanisms that operate immediately as soon as stars form and can efficiently operate even in dense gas, preventing supernovae from hideously overcooling in these dense high redshift progenitors of these galaxies. So with the last couple minutes, I want to make a point, though, that while I think some of these effects in the lowest order plane, this M-Gal-M-Halo relation, are being captured by the newest subgrid models, if you compare the new Stinson subgrid model that it sort of attempts to mock up some of these effects from radiation pressure, although I would disagree with the detailed way that they do it, perhaps, it actually looks fairly similar to our results in M-Gal-M-Halo. But I don't think that higher order diagnostics, like the structure of the IgM, actually look similar. So this is a simulation using a simple subgrid model and comparing it to a full feedback model. You can see the IgM temperature distribution looks very different. And what looks really different is the star formation history of the galaxy. So this red line is a no feedback run. Basically, this is the cosmological accretion rate onto the halo is the star formation rate. I put in a very simple toy model subgrid model that says for every unit stars I form, I kick out X units of gas. And I renormalize that, but I don't really change the shape. It still has this huge peak at high redshifts. And that's a problem. Even if I get the right stellar mass at Z of 0, this green and blue line are not what's observed in terms of galactic star formation histories. And things have changed qualitatively when I go to the full feedback model. A lot of material is blown out preferentially at high redshifts, and then it's in some sort of either local or supergalactic fountain that gets reaccreted at late times, so you end up with a much flatter or even late time rising star formation history. So finally, I want to just make a qualitative point that we haven't quantitatively investigated yet, but I think is going to be hugely important. Which is when you look at these simulations, so this is the same movie I showed earlier, you can plainly see that inflow and outflow are not cleanly separable. And I think most of us here doing the theory and observations have suspected this is true for a long time, but we avoid it in all of our modeling because it's nightmarish to think that we can't decouple inflow and outflow, that we can't say inflow proceeds completely unimpeded and outflow is just a separate term that takes some fraction of inflow and gets rid of it, basically. And that's essentially how all our semi-analytic models work. And the truth is, it's how most of our subgrid models that we're using for simulations of galaxy formation work. They're implicitly making this assumption that there's no coupling between inflow and outflow directly, and that we can separate those regimes. And you can actually just see in the movie how outflows smash into the inflowing filaments and change their structure. So, quantitatively, I don't know yet what that means and how much that revises of what we think we know about galaxy formation. But I think it's going to be very important moving forward with these more realistic simulations to understand those interactions. And I suspect those are going to depend in highly detailed ways on the microphysics, which, as I said, is by no means complete in these simulations. So I'll stop there. Thank you.
There's time for a couple questions, and then we'll have discussion later. So, Danielle.
You say that you have a single massive star for each stellar particle?
No, sorry. So the star particles are still, a few thousand solar masses for the Milky Way mass simulation. They get down to about 100 solar masses for the dwarfs. What I was trying to make the point is that we're not, averaging over many supernovae and dumping some integrated amount of energy in. Supernovae are discrete events, and the time and mass resolution is sufficient that you never have more than one supernovae associated with a given star particle and a given time step, right? Yeah. So it's stochastic explosions. So ideally you'd have 5 orders of magnitude better resolution to really resolve the dynamics of those individual blast waves. I'd like to, but of course we can't. But that's the step forward.
Charles?
Like, seeing the movies, there's a lot of breathing going on, side breathing.
Yeah. So.
Also, the star formation rates were flickering by quite a bit.
Yeah.
It violates the scatter.
No, so actually I had to skip this slide. So actually here's the star formation main sequence from these simulations. The dashed lines are the observed and the points are the simulations. And the scatter is formally a factor of 2. So it's a little higher for the dwarfs, but that's not a problem. What I was actually going to make the point with this slide is that actually this is a terrible diagnostic of feedback, because these yellow lines are simulations that have very weak feedback and very low resolution and hideously overcool, and they just move along the relation. They don't actually deviate from it very significantly. So that's not as much of an issue. The breathing in the movie is largely, I need to remake the movie. A little bit of that's real. A lot of it's the interpolation algorithm between the snapshots that I was making the movie from. So I should have said that when I was showing the movie. Particularly the interior of the galaxy doing that breathing mode was, yeah.
We'll have another question.
So connect to the last question.
Mm-hmm.
Although the breathing mode is obviously interpolation artificial, the star formation history still is quite light.
Yes.
Does this drive a significant response to the dark matter halo?
Excellent question. So Jose Onyorbe will talk tomorrow and show some more details of some of the dwarf runs where he's looked specifically at this. At the resolutions that we've explored, we're not seeing much of a core forming in those dwarfs. And we have a wide mass range spanning the range where, for example, the gasoline simulations see a big core. And this goes to the point that came up earlier, that this is very dependent on the actual details of feedback. Do you get in the gasoline simulations you can see in the movies, you get a lot of these super blowouts rather than venting, right? Where the whole ISM goes out and then falls back in. And so that creates a stronger response. Quantitatively I wish I could say more, but this is early days yet, so we're still looking at this. And I think understanding that difference, because I'm not, I wouldn't by any means say that this is proving that doesn't happen. It's just that for this particular model, we don't seem to see that level of response.